Hello everyone, welcome to lesson number 27 for BC Calculus, where we're going to talk about L'Hopital. And in this particular video, we're going to talk about the 5 other indeterminate forms that's not 0 over 0, infinity, or infinity. And most of the times, those indeterminates are going to be with transcendentals. So there are actually 7 different indeterminate forms for L'Hopital. In AB Calculus, we only talk about 0 over 0 and infinity over infinity. I'm going to break this into 2 different videos, and I'm going to talk about the 2 in this video and then 3 in the next. But before I get to the other 5, just a blast from the past, if you plug in 0, because remember, any limits that you guys do, you always want to do substitution first. That is the first thing you do for any limit that you have. If you plug 0 into the top for sine of 5x, you get sine of 0, which is 0. You plug 0 into the bottom, you're going to get 2 over 0, or 2 times 0, which is 0. So you get the form 0 over 0. So what you have learned, and in a second I'm going to show the answer key to this so you guys can just see it, is that you find the derivative top, derivative bottom, and keep plugging in until you do not get this indeterminate form. If you look at example number 2, we substitute infinity into the top, we get infinity squared. Well, that's still infinity, plus 5 still gives me infinity. Infinity plus e to the infinity is also infinity. So this is going to be 2 indeterminate forms that you guys have already seen before. So I don't want to make this video be these indeterminates, so I don't need to do that, but I just want to just pop up what the answers are for these particular examples, just so you guys can remember. Remember that formal notation for L'Hopital stands that you must say that the limit of your numerator is equal to 0. You must also say that the limit as your denominator is also equal to 0. Then you would say by L'Hopital, the function itself, the limit as x approaches 0 itself, will be equal to the derivative of the top over the derivative of the bottom. So you can take the derivative of the top independently, derivative of the bottom, and then if we substitute in again, we get cosine of 0, which is 1. 1 times 5 is 5, and then obviously 2. So this answer is 5 halves, which we actually have a property that we already knew the answer was going to be 5 over 2, because sine of ax over bx is just a over b. If we look at the second example here, infinity over infinity, again, we separate. We talk about the limit as x approaches infinity of our numerator is equal to infinity. This is our denominator limit is also infinity. Then by L'Hopital, we write our function out again. We take the derivative, as we see here. I did not show the next example, but if we plug in infinity here, we get infinity, and then we get infinity again. So this is another infinity over infinity. We would, in theory, write the limit as x approaches infinity of 2x is equal to infinity. The limit as x approaches infinity of 1 plus e to the x is also infinity. And then by L'Hopital, we go ahead and write 2 over e to the x. This is a bottom-heavy function, right? So this is going to be 2 over infinity. So 2 over infinity is going to give you 0. All right, remember, bottom-heavy functions always go to 0. So this is going to get bigger, smaller and smaller and smaller as we approach infinity. So that's just a really quick review of those particular examples. So let's get into what we're going to do in this lesson. There are 5 more indeterminate forms. In the video today, I'm going to do infinity minus infinity and 0 times infinity. So that will be the video that we're going to talk about here. And you're going to have 3 examples that I'm going to show you. In the next video, I'm going to do the other 3. So 1 to infinity, 0 to 0, and infinity to 0. So let's go ahead and talk about these examples right here. So the limit as x approaches pi over 2 to the left, of tangent of x minus secant of x. Okay, so tangent of x minus secant of x. When you're plugging in to your value, you have to visualize the tangent of x has an asymptote at pi over 2. As a matter of fact, secant has an asymptote at pi over 2, right? Because secant is 1 over cosine. And cosine of pi over 2 is 0, so 1 over 0 is undefined. But if we're looking at the behavior of our function, as x approaches pi over 2 from the left, then we know, and just really quickly, for tangent at pi over 2, we know our graph looks like this. Right, so this is what our graph looks like. This is pi over 2, this is negative pi over 2. So we're going to approach infinity. So this is going to be infinity. And the same thing can apply to secant as well. So we're going to also have infinity. So this is going to be an infinity minus infinity problem. Okay, so that's the idea of what we want to do for this problem. So we want to fix it. Now, usually when we do these problems, we want to transform this function to where we can get it into the form of 0 over 0 or infinity over infinity. That's the goal. That's really what we want to do for this particular problem. Well, let's do that. Let's do that. Well, the first thing I can do here is I can rewrite this as the limit as x approaches pi over 2 from the left. Well, tangent is going to be sine of x over cosine of x. And then secant is going to be 1 over cosine of x. And so this is going to be my function. So hopefully you guys can see where I'm going with this. Now, remember, for all limit notation, we're going to always keep limits, keep our limit notation as we go. And so this ends up being sine of x minus 1 all over cosine of x. All right? Now, when we do this, we plug in pi over 2. Well, neither of these are undefined at pi over 2. So if I just go ahead and plug in pi over 2, I get the right and left-hand side because they're continuous at these particular values. So the sine of pi over 2 is 1. 1 minus 1 is 0. The cosine of pi over 2 is 0. So we have 0 over 0. So we did exactly what we wanted. We transformed this into 0 over 0. Now, ladies and gentlemen, this just becomes good old L'Hopital. We would say that the limit, and I'm going to do this for this example, and then I'm going to stop doing it just because, it's going to get repetitive. And it's just, this video here is really just to make sure that you guys know how to do the problem. But yeah, so you technically would then say that the limit as x approaches pi over 2 from the left of the numerator is equal to 0. And you would say that the limit as x approaches pi over 2 from the left of the denominator is also equal to 0. And so this would be something that you would have to write out for L'Hopital. Then you would say by L'Hopital, or by L'Hopital's, it doesn't really matter which one you guys say here. We would then transform this. And so let's go ahead and do that. And, we'd say, so this here is equal to the limit as x approaches pi over 2 from the left, where the derivative of sine is going to be cosine of x. The derivative of cosine is going to be negative sine of x. We plug in pi over 2 to cosine, we're going to get 0. We plug in sine of pi over 2, we're going to get 1. So this is going to be negative, so it's going to be 0 over negative 1, which is going to give us an answer of 0. So this limit right here is going to be equal to 0. I'm not going to lie to you guys, most of these indeterminate forms, especially with these right here, most of them are going to be 0, especially for the infinity, finus infinity, and the 0 times infinity. Usually they're 0. Okay, so that's the first one that we want to talk about. So usually when it's infinity minus infinity, there's usually asymptotes. And most of the time, guys, you just probably want to, mostly they're going to be trig functions, and you would just want to rewrite them. Okay? Or just kind of, again, think about what I can do to get it back into the form 0 over 0 or infinity or infinity. That's the idea. So let's look at example number 4. And example number 4 says the limit as x approaches infinity of x times e to the negative x. So if we plug in infinity to our function, because we always going to do that, we're going to have infinity as literally in for x, and then we're going to multiply e to the negative infinity. Well, e to the negative infinity, you guys all know as 1 over e to the x. Sorry, I keep saying negative infinity. E to the negative x is equal to 1 over e to the x. So this is equal to 1 over e to the infinity. Well, this is a bottom-heavy function, so this is going to end up being 0, because if I take the limit of 1 over e to the x to positive infinity, this is going to go towards 0. So I have a case infinity times 0. So that's going to be the second of our 5 cases. So 0 times infinity. So you will always rewrite this. Now, 9 times out of 10, you're going to have some negative exponent here. So we chose, for this first example, something that's pretty basic and something that's fairly standard for what's going on here. We're going to rewrite this as the limit as x approaches infinity, and I'm going to just have x, and I'm going to drop this. I'm going to drop e to the x to the bottom. And that's straightforward. So if I plug in infinity now, I have infinity over infinity, right? So I've got infinity over infinity. So I know that I have the indeterminate form infinity over infinity. Again, ladies and gentlemen, the limit as x approaches infinity of x equals infinity. The limit as x approaches infinity of e to the x is equal to infinity by L'Hopital, blah, 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 blah. We're going to get the limit as x approaches infinity of 1 over the derivative of e to the x is just e to the x. And we're back to this whole song and dance here. We know that this answer is going to end up being 0. Okay. Most of these indeterminates, again, are going to be equal to 0. This next one will not be, but it's just a good way for it to do it. But rewrite, rewrite, rewrite. So infinity times 0. And most of you guys would have known to just rewrite this as x over e to the x anyways, and then just apply L'Hopital. So this is the case. Now, one that's maybe not as obvious to do is example number 5. So for example number 5, we're going to again plug in infinity right here. So we get infinity. And then we're going to do the natural log of 1 plus 1 over infinity. Well, 1 over infinity is going to be 0 because we're taking a limit. So this will be the natural log of 1. Well, the natural log of 1 is what we'd have. So it'd be infinity. Well, the natural log of 1 is a 0. So we have this indeterminate form again. So infinity times 0. We want to get it as a rational function. This is usually the idea between this one. So when you guys have 0 times infinity, you always want to make it a rational function. So we're going to absolutely do that. And usually you want to make the rational function you want the denominator to be either, if it's a negative exponent, that's sure anyway, or make it where it's something that's pretty easy to figure out or take a derivative of. So I'm going to go ahead and just move this down to x to the negative 1. So now I've got a rational function here. And so if I plug in infinity, I'm going to get 0 on the top, I'm going to get 0 on the bottom, right? Because I'm going to take the infinity. This again is going to be 0. 1 over infinity is 0. So the natural log of 1 is 0. 1 over x, the limit as x approaches infinity of 1 over x is also 0. So we're going to now take the derivative of these problems. So we're going to go ahead and do the limit as x approaches infinity. Well, the derivative of this is going to be 1 over 1 plus x over x. And it's okay to get a little nasty. It's going to work out. So it's 1 over, so the derivative of the natural log of a is just 1 over a times the derivative of a. Okay, so the derivative of a. And the derivative of 1 is just 0, and the derivative of 1 over x is negative 1 over x squared. And then this is just 1 over x. So we're going to also take the derivative of this, which is going to be negative 1 over x squared. Well, what beautiful thing happens, ladies and gentlemen, as you guys can clearly see here, is that these are going to cancel out with each other. Please watch your signs. Be careful with your signs here. They do actually cancel out as well, but just be really careful with that. So now what I have in this problem is the limit as x approaches infinity of 1 over 1 plus 1 over x. I already know that this is not going to be another, I don't have to take the indeterminate again because I've got a 1 in the top. If I plug in infinity here, this again becomes 0, so it's 1 over 1, which is 1. So this limit is going to be equal to 1. All right, so in these particular examples, when it's infinity times 0, you really want to get it as a rational function. And you already know that because we want to get it into the form of 0 over 0 or infinity over infinity. So rational is what we want. So we get that. Usually it's going to have some singleton x. That's what's going to usually be our infinity, or x squared, or whatever it is. Some value of x. Move it to the bottom, change the sign, take the derivative top, derivative of the bottom, and then hopefully it's going to work out where you guys get a very easy derivative. All right? Which sometimes should cancel out, right? That's the whole point of this, is to cancel things out. So where you're able to substitute in, you don't get an indeterminate again. And if you get an indeterminate a second time, you do it again and over again. So that's my video on 0 times infinity and infinity minus infinity. We're going to come back in the second video for this lesson and talk about our friends 1 to infinity, 0 to 0, and infinity to 0. So I'll see you guys in the next video.